doctor Nat Gopalswarny, pero bueno, déjenme intentar nada más resaltar algunas de las muchas cosas que ha hecho. Y bueno, quizás la mayoría aquí saben que él está concentrado en la física solar y en la física de la relación Sol-Tierra, pero particularmente su interés está en las eyecciones de masa coronal y en el impacto que tienen las eyecciones en la Tierra. Digo, es notable, ha publicado más de 400 artículos y ha acumulado una serie importante de descubrimientos a lo largo de su carrera. Aquí anoté algunos, por ejemplo, CMS a altas latitudes, la deflexión de CMS por hoyos coronales, la aceleración efectiva de las CMS, la expansión anómala de las CMS en el ciclo solar 24. Y bueno, ha estado activamente involucrado en coordinación, organización de talleres como SHINE, CDAW, SCOSTEP, COSES, Varsity y el Año Geofísico Internacional recientemente. Y bueno, ha recibido múltiples premios a lo largo de su carrera, y al menos el último que tengo aquí en mis registros fue que la NASA le dio la medalla a liderazgo sobresaliente en 2013. Y bueno, démosle la bienvenida al doctor Nat Gopalswarny. Thank you, Nat.
Gracias, Alberto. Buenos días. And there my Spanish ends. I'm going to talk in English, of course. So this talk is about coronal mass ejections from a novelty to a natural hazard. Basically, this is more like a history of CMEs rather than too much physics. So pardon me for that, but I think it's very important to understand the importance of the path which was taken in identifying the CMEs. And we now don't understand 100%, but we have an excellent idea of what these things are. So I want to take you through this path over a period of about 300 years. So of course, in this work I've been doing, a lot of people, of course, I collaborated with, including two people from UNAM, Alejandro Lara and Ernesto from Morelia. Hola, Ernesto. So it's a great pleasure for me to be here. I was here and probably gave a talk some 15 years ago in UNAM. A similar seminar, but I was here last year in October for a SCOSTEP varsity meeting. And then at the time, I had the opportunity to meet Alberto. And so he suggested that I could come here and give this talk. And I was happy to accept it. And also, I thank Alejandro for arranging my logistics and also the excellent trip I had to Hawk yesterday. So I was able to go all the way to the top and feel the instrument and also the ambience over there. All right, so as you all know, any scientific discovery doesn't just typically come with a long history. People have poked around, they try to find there's something going on, and they have some hunch, but they could not prove it. So the CMEs is, in a sense, it's like that. There's a long history. But the CMEs in white light was discovered only in 1971. That's very recent, and that's why I call it a novelty. But before that, people knew how sun affects Earth. People knew about geomagnetic storms. People knew about flares. But people did not realize the CMEs are the most important cause of space weather, the hazardous space weather. And that dawn happened only just 2 decades ago, in the mid-1990s. Before that, everything was attributed to solar flares, but now we know in more detail how CMEs affect Earth. So this is basically my outline. I already talked about it. So I just wanted to start with, instead of going through the history, I wanted to start with some CME observations so you can understand the context, what I'm talking about, and also what I mean by by natural hazard. So this is a movie from the Solar and Heliospheric Observatory SOHO mission. And what you're seeing is a large area around the sun. So this green area is the sun, and you see a coronal hole on the sun. And this is the occulting disk, which produces artificial eclipse. So you can see the corona, because the sun is a million times brighter than the corona. So normally you don't see it. When you see the sun, you just see the photosphere, and that's it. But when you block the photosphere, you should be able to see the corona outside the sun. And of course, this was originally known from eclipse observations, where you can see all these beautiful streamer structures around the corona. And people knew about eclipses probably from the time of Babylonia. You know, they even computed the time of eclipses and so on. So it's not new. But now we are able to see the importance of this corona and how it affects Earth. So this is the equivalent of a moon, right? Moon blocks the sun, so you can see the corona. But now we have to make it bigger, because man-made instruments are small, a lot of scattered light, so you have to make the occulting disk a little bit bigger. That means you cannot see all the way close to the surface of the sun, but still you're able to see most of the dynamics that we are interested in. So in this picture, you see the image from SOHO, and then we have superposed an image from SOHO's EUV imager. So you know what's going on the sun simultaneously. And so you see two things happening here. There's a small eruption here, and there is a big eruption from here. And then after the eruption, the whole image looks all degraded, because these eruptions produce a lot of charged particles. Those charged particles travel in, within tens of minutes and come and hit the detector of the instrument which is making these images. So the detector kind of saturates because of all these particles, and the image is already degraded. So it's a direct demonstration of space weather. So we want to observe the corona, but the sun produces some eruption, it spoils the image. Okay. And then the right-hand side, I've shown some plots from the GOES X-ray observations. So GOES observes in two wavelengths, so 1 to 8 angstroms and 0.5 to 4 angstroms. This is the lower range, and this is high range. And what you see are these fluctuations. These are the solar flares. And solar flares were known from 1859. But now we get most of the information from soft X-rays, because they are much more sensitive than optical observations made in white light or in H-alpha. So what you see here is when the eruption goes on, you see a big enhancement, right? At the same time as the this eruption, you see this big enhancement in X-ray emission. So that means there is a close relationship between CMEs and flares. They are kind of two different aspects of a solar eruption. It is not that flare produces CMEs or vice versa. They are just two different manifestations of energy release from the sun. So one of the points that I will make during this meeting is that there is a better understanding of the relationship between CMEs and flares now, because in the past people thought about CMEs are produced by flares and vice versa. And you can find some 25,000 movies like this in our website, which is listed here, c.gsfc.nasa.gov. And if you want to look at it, want to see on your birthday how many CMEs happened, you can go and look at it. You have all those information given here, movies like this. And also there are many different types of combination of movies you can see there. For example, this can be blown up into bigger image and to see what's going on the sun and so on. So this is a snapshot of the previous movie when the two eruptions are going on. So you can see this this faint structure is the CME here, which contains a very bright core inside, which we know now are prominences, solar prominences, which are ejected from the sun. and they form the inner part of the CMEs. And then here you see a bright spot here, that is the solar flare. And then overlying the flare region is this huge structure, which we call the CME. And also the overlying streamer structures are bent around here, see? So it comes out like this and bends here, comes out like this and bends here. That is because there is a bow shock sitting in front of the CME, because the CMEs go with the travel speeds exceeding 2,000 kilometers per second. So you have, it drives a shock, and that shock is what we are seeing here. So these are all the internal structures. You have the prominence is similar to here. This is the prominence, and this is it's actually a magnetic structure. Now we know that's a magnetic structure. And you can see that this is huge compared to the size of the sun. And now we know that this kind of extends all the way to Earth. You can actually detect them. If you have a spacecraft up there, they can actually see them blowing past the spacecraft. Not only, so that means the size can be as big as 1 AU, the CMEs. Not only that, the size can be as big as 100 AU, because these CMEs continue to travel, go all the way to the edge of the solar system, bump the termination shock. And big CMEs can actually make the heliosphere breathe, go back and go out and come back in. So these CMEs are really the most energetic phenomena in the heliosphere. And of course, if you in the interplanetary medium, if you have instruments, you can detect them directly. There are also other means of detecting in the interplanetary medium. For example, a MEXART can observe the CMEs en route to Earth or far away from the sun. So there are many different ways in which you can observe these CMEs. And their impact. So here is another movie of this, again from SOHO. You see this is the sun here. This is the occulting disk. This is the pylon which holds the occulting disk in front of the telescope, so you can block it. And you see, again see this huge eruption, 2 eruptions. Say one there produces all the particles, and then the second one again produces particles. And these are happening at the center of the sun, and within a day they arrived at Earth, because they are so fast. The speed was more than 2,500 kilometers per second. Okay, so they can cross the entire Mexico in a matter of seconds. So fast they are. And then, so when you look at the particle flux, say observed by Gross, you can see for a period of 2 weeks, Earth is immersed in very high energy particles. So you have a lot of spacecraft out there. They're all affected by these kind of particles. So this is the red is 10 MeV, 50 MeV, and 100 MeV particles, and their level remained high for 10 days, at 2 weeks. And so these 2 arrow marks, the red one and blue one, mark the 2 big CMEs that are coming from here. But there are also other CMEs from this region which produced more particle events. So the net effect is you had a high level of particles for 2 weeks. So how about geomagnetic storms? You know DST index, which measures the change in the horizontal component of the Earth's magnetic field. And you can see that normally it is like this, but these 2 CMEs cause this big depression in the horizontal component of the magnetic field. So these are called the geomagnetic storms, and these are called the particle storms. So both these are natural hazards, because both of them can lead to a lot of bad effects, including, for example, if you go on an airplane in a polar route, these kind of particle events can affect both crew and passengers. They increase the lifetime dosage for a person, because you get high energy particles penetrating people in the airplanes. And then geomagnetic storms once again produce accelerate particles in the magnetosphere, and you get aurora. You also get magnetospheric satellites affected by these particles. And then they can also induce currents in the ground. You have geomagnetically induced currents which can blow off pipelines. And during these events in Sweden, a transformer was kind of boiling, and the power was lost for 50,000 people in Sweden during these events. So that's why I call this as natural hazard, and similar to maybe earthquakes or volcanoes, there are a lot of other things. This can also cause affect society and life. All right. So the last one I wanted to show is that the CMEs affect not only ground technology, also interplanetary spacecraft. This is an experiment called Marie on Mars Odyssey spacecraft. The idea of this instrument was to measure the radiation environment of Mars. So in the future, we can send spacecraft or humans to Mars. So we want to know what is in there. So this is kind of like a scouting trip. And one of the CMEs, which I showed in the previous movie, basically took this instrument off. The particle radiation from these CMEs took this instrument off. So basically that instrument was lost. And then in the next, the year before, in 2002, Japanese sent again another Mars instrument called Nozomi. By the way, Nozomi means hope in Japanese language. And so there was another big CME. Sorry, this looks distorted, but anyway, this is round sun. There's a big CME coming off from here. It produced particle events, and you can see again the destruction of the image, indicating a big particle event going on. And this basically disabled Nozomi. So Nozomi became hopeless because of this event. So essentially, CMEs don't care whether Japanese or or Americans or Mexicans. They all affect. So that's why it's really a natural hazard everybody should worry about. All right, I want to end this small section of my talk by showing one CME that had all these various components. And in addition, you can see some connection between all the way from the sun to Earth. So I'm showing again a SOHO image. That's the sun. That's the corona. It's a difference image. You can see what's the variation on the sun. And there is an eruption going on near the disk center. And within half an hour, you see a huge CME. We call it a halo CME because it appears to surround the sun, but it's not really surrounding the sun. It is just in projection because it's coming towards us. So in sky plane projection, it appears as if it is surrounding the sun. So we call them halo CMEs. And then immediately, as soon as the eruption takes place, you have the particle increase by several orders of magnitude, and then this is the increase near the sun. And as when the CME comes towards Earth, you have another big increase in particle intensity. You can see 10 MeV, 50 MeV, 100 MeV, so it's a big event. And then when the CME passes SOHO spacecraft, it observes a big shock. You can see the speed jumping from here to here. That means it's a big shock going on. And then in radio, we have low frequency radio observations made by wind spacecraft. It has got an instrument called WAVES. It can detect radio emission from 14 megahertz down to about 20 kilohertz. Okay, and this radio emission is very low frequency, at frequency below the ionospheric frequency, so you cannot observe them from ground, so you have to go to space to observe them. The good thing is if you observe from space, you can see very low frequency, and the low frequency means farther away from the sun, and you can actually track these radio bursts all the way. So that's the kind of sun, and here is Earth, so you can track them all the way until they hit Earth. So there are some techniques by which you can track the CMEs all the way from sun to Earth. And also this was associated with a big geomagnetic storm, and I don't know you can see this. There is a sudden commencement here, spike here, and then the geomagnetic storm. Can we get the lights off? Because this is completely dark. Can anybody see the DST index here? Yeah, so it just is here, spike, and then goes down like that. All right. So if you look at the interplanetary plasma observations, you can see this event very nicely. So this is the, for example, DST index, you cannot see here, but you can see it here. So it's normal, and then suddenly goes up. That's the sudden commencement, and goes down. That's the geomagnetic storm, and recovers over a day or so. And that's the same as this one. And so essentially the CME observed here is observed like this at 1 AU, because we have only one-dimensional observation. We pass through the CME, and then you see the shock first, and then you see this what you call magnetic cloud is the CME in situ observations. So essentially this bump in magnetic field is caused by the CME impacting the spacecraft. So this event demonstrates that it's a really huge thing. Something happens on the sun, and it travels through the interplanetary medium in a matter of a couple of days, or sometimes even one day, and then affect the spacecraft that are in the neighborhood of Earth, and then go past Earth and affect other planets also. So if you have a planet, another planet hosting a spacecraft, you will see the impact of the CMEs. Okay, so to summarize what I said so far, CMEs are large-scale magnetic structures erupting from the solar corona that can cause major changes in the interplanetary medium and impact Earth and other planets. They accelerate particles near the sun and in the interplanetary medium. They cause geomagnetic storms when they hit Earth. And both these effects, namely geomagnetic storm and energetic particles, can affect technology both on ground and space. All right, now we go to the main part of the talk, the history. So you all might have heard about Galileo's telescopic observation of sunspots, but sunspots, of course, were known from the Chinese records from BC. 364 BC is a very well-known record of sunspots. But I think in the modern times, Galileo's observations start the real scientific observations. And around that time, people already knew about variation in geomagnetic field. And geomagnetic disturbances and aurora connection were known again by mid-1700s. The important step in the connection between sun and earth happened at the time of Willam Herschel. Many of you know as a famous astronomer, but he also did something about solar physics. So I'll come back to that. It's a very interesting story. And then von Humboldt, he coined the term magnetic storm in 1806. And then you have this famous Carrington observation of a solar flare, observation of prominence eruptions, and finally Hale discovering the magnetic field in sunspots. So far there is no magnetic field only in the case of Earth, but in about the sun, first time we know that sunspots are magnetized when Hale observed in 1908. And then we have cosmic rays discovered in 1912 here. I didn't put that in here. But the worldwide decrease in cosmic rays was discovered by Scott Forbush in 1937. And then Newton, this is not the same Newton, Apple Newton, this is a recent Newton. He estimated that there must be something coming from the sun that is producing geomagnetic storms, and that is actually relevant to what we are going to talk about, CMEs. And then Forbush first time reported the detection of solar energetic particles, only in 1946. Then a year later, we had a very important discovery in radio, type 2 radio bursts observed by a lady by name Ruby Payne Scott in Australia. And then a theoretician in 1953 proposed that the sudden commencement in geomagnetic storms is actually caused by an interplanetary shock. That's the first time he's proposing it. There was no observation at that time, but he proposed it. And then in 1957 was a discovery about a moving type 4 burst. This is a radio burst moving away from the sun implying there must be some plasma structure moving away from the sun. So you can recognize that there is some relevance to CMEs again. And in 1960, for the first time, the 4-Bush decrease was detected in the interplanetary space, not from the ground, in the interplanetary space. From that, they realized that there must be some plasma coming from the sun which blocks the cosmic rays, and that is called 4-Bush decrease. And in 1962, the Mariner 2 spacecraft detects interplanetary shock. 10 years ago, it was proposed by Tommy Gold. And then, of course, after this, you have 1970. There is a very important ground-based observation made from Hawaii by Hansen et al. And they found the connection between the moving type 4 burst and a K coronal change. Suddenly, a streamer that is sitting in the corona disappeared. And he associated that with some kind of transient event happening on the sun, which in the next year, it was actually confirmed as the CME by OSO 7 spacecraft. So this is the brief history. So now I'm going to say a few things, expand some of these things, and bring you back to the level where CMEs are completely observed in white light. All right, but I just wanted to show this history about Wilhelm Herschel's observation. I think this is a very important event in the history of solar terrestrial physics, but like many other important discoveries, he was ridiculed for that. So in 1801, Herschel reported to the Royal Society that 5 prolonged periods of few sunspots correlated with wheat prices in England. Okay, you have low sunspot number, high wheat price. Looks like some kind of wacko. Nobody believed him. He reported it. It's a long paper, actually. It's available online. If you go, you can read it. So he inferred that less number of sunspots indicated less heat and light from the sun. So wheat production was low. When wheat production is low, the prices have to go up. That's perfect explanation. But you know, we know now that when you have more sunspots on the sun, there are more bright plodges around the sun, and the irradiance TSI increases, right? So there is more output, electromagnetic output from the sun. That means more photosynthesis for the plants. I think it's an excellent observation, but he was ridiculed. And also, there's one more interesting thing is the Sunspot Cycle. He noticed periodicity in this wheat price going up and down, and correlated with the up and down of the sunspot number. So I think, of course, Schwab is credited with the discovery of solar cycle in 1843. It's about 40 years before Herschel already noted, although he didn't study that aspect of it. And here are some pictures showing the sun with, so here's a sunspot, and the sunspot comes with a plodge around it, and this is also a region of high magnetic field, and bright, that means it produces more radiation. So the less radiation due to sunspot is more than compensated by the more radiation coming from the plodge region. That's why during solar maxima, you have more radiation coming from the sun. But you know, at this stage, of course, sunspots were not known to have magnetic field or any connection to CMEs or flares or anything. But this is one very good example of solar terrestrial relationship. And also, it connects 2 different aspects, namely the magnetism, which is sunspots, and also the irradiance due to the enhanced irradiance due to the plodge regions. Okay, so I already mentioned this is Alexander von Humboldt. There is a fellowship in Germany on his name, you probably know. So he was one of the pioneering scientists who published a lot of stuff, and one of the studies he made is the connection between aurora and the change in the magnetic field as observed by the magnetic needle he had. So based on this connection, he coined the term magnetic storm. And so he also did some very interesting thing. by convincing the Tsar of Russia and also the British Empire that they should put magnetometers all around the world to measure the global influence of the magnetic storms. And he did find that the magnetic storm is not local, it is global. And I showed you the DST index before. The DST index actually is a global index. You make the horizontal field measurements at many observatories around the equator and then average them to get the DST index. And then, of course, this famous observation by Richard Carrington on September 1, 1859. He observed this. This is a sunspot, and so he saw this horn-like features, which are basically brightening, which lasted only for a few minutes, and they are basically the white light solar flares that he observed in 1859. The most important thing is, within about 18 hours, there was a big geomagnetic storm. And this geomagnetic storm affected telegraphy, which was the technology those days. But he was very cautious, saying that, okay, this may be coincidence. I think now we know that this big eruption on the sun caused the geomagnetic storm the next day within about 18 hours. The sunspots, of course, were known. The first recorded drawing of sunspot comes from John Worcester on December 8, 1128. It's 1,000 years ago, almost. It is, of course, much before the telescopic observations, which began in 1600s by Galileo and so on. And you can actually see the drawing has the umbra, the penumbra, and he also saw probably on both hemispheres of the sun. All right, so now we looked at flares, we looked at the sunspots, and now prominence eruptions. So prominences can be seen now. Of course, many of you might have seen solar eclipse. During solar eclipse, you can see these prominences sticking out at the limb. And this was actually noticed by Russians as early as in 1185. In a chronicle of Novgorod, they noted that they look like red amber, like horns from the sun, so which is during an eclipse. So it's clearly they already detected prominences as early as 1185. And so here is a modern observation of a prominence eruption. So that's it's a big prominence going off. This is observed by the Nobayama radioheliograph. But as far as 1868, the routine observations were made during eclipses by Johnson and Lockyer, and they constructed an instrument as we call a spectroscope, and then they were able to observe prominences even outside eclipses. Then the routine observations began. 3 years later, Secchi classified active and quiescent prominences. So some are sitting idle and some are shaking up. And then Father Gyula Fenyi from Hungary, he actually measured these prominence eruptions. The speeds can be exceeding 100 kilometers per second. 100 kilometers per second. So this is the fastest motion that they could observe near the sun those days. And as I showed before, the prominence eruptions now form the interior part of CMEs. So in this case, there is a big CME around the sun, around these prominence eruptions. So I think by the end of 19th century, you have a lot of interesting ingredients of real motion from the sun already discovered. Okay, so the important observation by George Ellery Hale in 1908, he discovered that sunspots have magnetic field. And also he observed a lot of flares using H alpha, and he is similar to von Humboldt. Hale set up H alpha observatories all around the world. So that is called flare patrol, even now that is used. And these flare telescopes were able to monitor all the eruptions going on the sun. And he, of course, connected the flares and the geomagnetic storms. And he even measured the average delay between the eruption at the sun and the geomagnetic storm is about 26 hours. Of course, the mechanism was not known. It's only 2-point observation. You observe something on the sun, you see a geomagnetic storm, and you say there must be some connection. But later on, you had Newton, who made this connection, and he assumed there's some kind of stream, corpuscular stream coming from the sun causing the geomagnetic storm, and he estimated that stream should have a width of about 90 degrees. So that's now we know that's the size of the CMEs we observe now. So there are some hints already. And here is a very nice observation from Hale in 1931. So you can see in H alpha, is this H alpha ribbons, which we call. This is a very good indication that a filament that was lying between these two erupted, and that is an indication of a coronal mass ejection. But of course, they simply connected this flare to the CME, but now we know the connection is because of a mass ejection coming from this region and coming and hitting Earth. And this is a plot from Newton, and you can see that this is the sun, and you see a lot of dots here. These are not sunspots. These are the locations where the flares happened, and then they observed a geomagnetic storm associated with them. So the open circles are small storms, the filled circles are large storms, and then the filled circle with this surrounding circle are outstanding events, historically known from the time of Carrington. So we can clearly see that you have to have an eruption happening near the sun center to have a big storm. And that's very nice observation, because if there is an eruption happening on the sun, because Earth is projected to be here at this location, right? So some eruption happening directly coming towards Earth. That is the inference from this plot. So now let's move on to again something which is different from the solar physics. It's more to do with cosmic rays, and this guy, Scott Forbush, he had discovered this Forbush decrease. So you have a normal level of cosmic rays, and suddenly cosmic rays decrease, and we call this as Forbush decrease in 1937. But in 1946, he published a paper in Physical Review Letters where he found this spiky increase in particle intensity, so which he called solar cosmic rays. You see 3 of these. First time he observed in 1942, probably he didn't know what it was, and then in 1946 he realized that this must be something to do with the flares, and there was in fact associated with this event, there was a solar flare. You see the 2 ribbons in H alpha, very close to the sun center. So there must be CMEs coming from this region and coming and hitting Earth, but he did not connect the in-between thing, but he thought this must be something to do with the geomagnetic storm. And you know, geomagnetic storm is caused by the ring current enhancement. So he connected the Forbush decrease to the ring current, and then you have the sudden commencement, right? So you know, the geomagnetic storm starts after the sudden commencement. It's natural to have a temporal association. But the important thing is this spikes, which he associated with solar flares. So that means solar flares are responsible for big particle events. By the way, these are observed from the ground, so the particles can penetrate the atmosphere and come all the way to the ground. And we call them now as ground level enhancement events, GLEs. So these are basically particles with energies as high as few GeV coming from the sun. So this is the first time people detected high energy particles from the sun. Next year, the very next year, there was a radio observation from Ruby Payne Scott. She found a pattern. So she observed in 3 frequencies, 200, 100, and 60 megahertz. At 200 megahertz, there was a burst first, and in the 100 megahertz, it was delayed somewhat, and in 60 megahertz, further delayed. So it looks as if something was propagating away from the sun, because near the sun, the plasma density is high. So somehow this frequency is related to the plasma frequency. That's why You have earlier emission at 200, later at 100, later at 60. So she even estimated some kind of speed, something like 500 to 750 kilometers per second, and she correctly identified that the derived velocities are of the same order as that of prominence material. You remember I showed you previously from 1800s there was an observation from Father Guillaume. He observed hundreds of kilometers per second speed for prominences, and she made that association. So there's an interesting thing is this is 1 year after the report by Hay about jamming of the British radar by the sun, right? So 1942, British radars were jammed and they didn't know what it was. Hay correctly identified them and then published them in 1946. So the very next year, this discovery was made. We now know that these are called type 2 radio bursts. These are caused by shocks driven by coronal mass ejections. So, but we started with some kind of motion, and we are going to build the story. But this time, I want to tell the story of Ruby Payne Scott. She was actually working in Australia, and in Australia those days, in the early 1900s, there was a law that women who are married cannot work. Okay, so she hid her marriage. She had kids, but she was hiding her marriage and continued to work when she made this discovery. But like smart people do, they finally found out she's married and fired her. She continued to work as a teacher afterwards, and she was a very progressive woman. And it was a very interesting story that a librarian of the institute, said that women should have dress code and stuff like that. Then next meeting, she went with shorts and sat in the front. I like her attitude. So, and then in 10 years later, André Beauchot from France, they had this radio interferometer, and he found some interesting. It was only one-dimensional. These are, for example, this is the sun in one dimension, and these are the radio bursts. And he found a burst which moved from its original location. Look at this B. Okay, it's one-dimensional, so you can see this B source increase in length from the sun center. So he inferred that must be a moving type 4 burst. And later on, there's a very nice observation made by our old friend Ed Schmal, another two-dimensional observation of a radio burst. So this is the sun, it's a radio burst location, and you can see the distance of this radio source increased as a function of time, and from that they could infer a speed of about 350 kilometers per second. So this probably is a very direct observation of a plasmoid moving away from the sun, carrying energetic particles and producing radio emission. And this is Tommy Gold, and he's the guy who proposed that the sudden commencement of geomagnetic storms must be due to an interplanetary shock. Of course, by the time you have some indication from the sun, the type 2 radio bursts can be due to shocks, and also he inferred, based on the sudden nature of this, it must be a shock. And so this is his picture, which he made several years later, where so this dot is the sun, and you have this structure which he assumed as a magnetic bottle carrying some kind of solar plasma called solar gas, and then driving a shock. And this shock is the one which causing the geomagnetic storm, which is a very good explanation before any of these observations. And around this time, of course, the idea of shocks already known. There's Mhd Shock Theory by D. Huffman and Teller. You probably know Huffman-Teller frame and stuff like that. So they already knew about shocks. And also Parker applied this Huffman-Teller theory to interplanetary shocks in 1963. Also in 1957, Parker proposed that magnetic clouds may be ejected from a magnetic field with speeds as high as the Alfvén's velocity. Now this is basically what we use from the flare side. When there is a reconnection, you have a reconnection outflow at the Alfvén speed, and that's what is the interior part of the CMEs. So he had an idea that there must be ejections from the sun and they should be magnetized. So based on all these solar radio observations, Fokker in 1963 drew this picture. So type 2 radio bursts caused by the shocks, and these shocks are driven by magnetic bottles like this, and these are the ones which produce the type 4 bursts. This is pretty close to what we know about CMEs. There's a CME and driving shock. So that was a nice picture. This basically using radio observations, and also there is a similarity between this and what Gold did in 1962, right? I just showed the picture turned here, and you can see the similarities. This is near the sun, and this is in the interplanetary medium. So there is this is in 1962, about 10 years before the discovery of white light CMEs. And then a very important discovery came by Fan et al. Using the Pioneer 5 observations. You can see this is a plot of particle counts, and this is a plot of magnetic field in the interplanetary medium. So they noticed that there's a big drop in the particle intensity at this time associated with the sudden commencement, and that is the 4-Bush decrease. It looks similar, but the low resolution, but it's very similar to the plot which 4-Bush published. And then following that, there was another particle event. They are not connected, but they observed a big particle event also. More importantly, there was the magnetic field observed by Pioneer showed an increase up to 50 nanotesla. This must be a pretty big event, because we know now in magnetic clouds, the interplanetary CMEs, the magnetic field can be as high as 50, 60 nanotesla in a very big events. But so this is what is the cause of the 4-Bush decrease. But before that, there was a little bump here, and that probably is a shock. Their resolution is not good enough to identify that as a shock. So this so happened that the CME, the magnetic field part, got discovered first, then the shock. So I just wanted to show this very nice observation from Hawk about 4-Bush decrease, and you can see similar decrease going down. And so I just decided to insert this slide after my visit to Hawk yesterday. So, so this decrease is caused by CME, we know very well now. And so that was the important contribution made by Pioneer 5. That's the spacecraft. Okay, now in 1962, Mariner 2 detected the interplanetary shock. Mariner 2 was located here compared to the sun, and here is the Earth. So there was an event basically going about 36 degrees behind Earth in this direction, and he was correctly able to point out that there should be a sudden commencement following this, but because the event was going not directly hitting Earth, there was actually sudden commencement, but was only very weak. You can see here. That is because there is no storm, because the CME itself did not hit Earth, only the flank of the shock hit Earth. So this was the next important discovery in 1962 about the shock, and so Tommy Gold definitely was happy. His prediction was verified, and around this time he also had a couple of interesting ideas. One is the particle acceleration by the shock near the Earth. When the shock passes the spacecraft, there was an enhancement in particles that we know as energetic storm particles, because that also happens around the time of geomagnetic storms. So they thought geomagnetic storm has something to do with the particle increase, but now we know it is because of the shock. And U.R. Rao in 67, he proposed that the particles you're seeing when the shock passes by Earth is actually particles accelerated by shocks. And of course, around this time, people already knew about particle acceleration by shocks for cosmic rays and stuff like that. All right, so this summarizes this part of the talk, which shows that there are many different discoveries, something like bits and pieces of the CME made over several decades. So you had the type 4 bursts coming from the magnetic bottle, eruptive prominences happening close to the sun, but here solar flares, type 2 radio bursts from the shock, and 4 burst decrease behind the shock, and then sudden commencement due to the shock, and so on. So this conceptual drawing made by Tommy Gold, and also a similar picture made by Fokker in 1963, have an excellent resemblance. That means to a modern CME, that means the CMEs were waiting to be discovered. Okay, these are all observations which are not in white light though. So then comes the white light observation made by Hansen et al. In 1971, and here is the observation. So this is a plot of position angle, so just going around the sun over an arc of about 80 degrees here. So 40 degrees means it is something like if you look at the clock angle, 40 degrees is like around 11 o'clock, and then 120 degrees is past the 9 o'clock mark and coming a little bit below. So this is basically going around the sun over about 80 degrees, and look at these numbers. There's 1, 2, 3, and 4. So over this time 1, 2, and 3, there is an enhancement in white light intensity in the corona, and then suddenly it dropped. This is at 1.25 solar radius from the sun, and this is at larger distance, 1.5 solar radii, and you can see this big increase and then sudden drop. So increase and drop, which actually you can see it in this plot better. This is time, and this is K coronal intensity. So the intensity was building up and then suddenly dropped. Associated with the sudden drop was a big moving type 4 burst. So now you see the connection. There is a moving type 4 burst as something disappears in the corona. So he called it a coronal transient. And if you look at the streamers, actually there was a streamer like this sitting above the east limb of the sun, and this is the structure which disappeared, causing this kind of signal. And these dots represent the moving type 4 burst. So there is already a first white light indication that there must be something, a transient phenomena happening on the sun, and associated moving type 4 burst, and he called it a coronal transient. And to a modern observation would be like this. This is a coronal observation from stereo core 1, and here is a streamer, something similar to this one. Okay, and then from this time, this frame to this frame, you can see this kind of brightened up. So it's going up like that, and then it's dimming here because something is moving out. See, here's a CME, and then so this here you see a void, dark, and dark is because the brightness decreased. So it's a correct identification, but of course they did not see the CME moving out. And then came the final observation by the OZO 7 spacecraft. They had a coronagraph on board, and so here is this. So the occulting disk, you're looking at the lower left quadrant of the sun. So sun is like this, and you're looking at this quadrant. So that's the corona, and you see a streamer structure, something similar to what I showed in the previous, and here, and then something happened here. So compared to this one, this is broadened, and something else happened here. So this guy, David Roberts from Naval Research Laboratory, thought that he was a technician, and he was in charge of the camera, and he thought something failed. So the camera is failing. You see funny structures in the image. But when he took it to his superiors, Gunter Bruckner and all these Team Kuhlmann and Tausi and all these people, they recognized it. This must be a coronal transient, and that is the first time you can see something moving out from here into the corona, and they, of course, confirmed it as a coronal transient. Since then, there are many, many coronagraphs. You have Skylab, Solwind, chronograph polarimeter on SMM, SOHO LASCO, Stereoseki. All these, of course, now have accumulated wealth of information. Now, tens of thousands of CMEs have been observed. And so now we know a lot more about CMEs because of all these observations. So I will briefly go through some of these chronographs and show you some key results that contributed to the current state of knowledge on CMEs. So after OSO 7, which operated only for about 3 years, it observed only 20 CMEs, 23 CMEs, I think. Yeah, 23 CMEs. That was, of course, now you know how many CMEs are observed by SOHO, 23,000 CMEs. So it's 3 orders of magnitude more. But that was very important at the time. And even with this, with few CMEs, let me skip that. People came up with ideas. So, for example, Marty Kuhlman in 1974, he identified the CME to be the Gold's bottle, the magnetic bottle that Gold drew behind the shock, and he identified them with that. And then there was another paper by Ron Stewart from Australia. He pretty much did everything like the Fokker plot here. So he found the leading edge of the plasma cloud. He found a type 2 burst like this ahead of the cloud, and he found a bright structure behind associated with H alpha prominence, and that is the interior part of the CME. There was a moving type 4 burst associated with this interior structure, and so on. And they had different, height. This is height versus time plots. So it's a pretty similar to what this plot was already confirmed. And then next mission was the Skylab. That is the first space station, as you know. It operated from 73 to 74, just a year or so, and it observed 110 CMEs already over a period of less than a year. And this is a picture taken by Skylab, and they called at the time as a newfound cosmic phenomenon, as CME. And it's definitely interesting, especially if you play movies. You can see so fascinating because it's a lot bigger than the sun itself. That's why they call it newfound cosmic phenomenon. And if you know, if you have seen stereo movies now, you can really see their cosmic phenomenon, because you can see these CMEs moving in the interplanetary medium, and you see all the stars and Milky Way and everything in the background. So I think it's really, truly a new cosmic phenomenon that they talked about. And of course, there are many, many discoveries from the Skylab. The name from coronal transient became coronal mass ejection. I've seen names like coronal transient, coronal mass ejection transient, and coronal mass ejection. I think Jack Gosling is the guy who made the name to coronal mass ejection in 1975. And very important connection, he made the connection between white light CMEs and the interplanetary shock that was observed by another spacecraft. And also Hillner et al. Showed that the CME rate is related to the sunspot number. So there is a solar activity connection to CMEs, so there are more CMEs coming from solar maximum. Now it is very obvious because you have more magnetic field structures on the sun, they erupt to produce CMEs. And then also there was an important paper by Kaler et al. Who showed that the solar energetic particles are due to acceleration by CME shocks. So this is somewhat related to what Rao et al. Did in 1967, but then at that time, of course, they did not know the shock was due to CME, so he's the one who showed the connection. And the idea that CMEs can be magnetic flux ropes was proposed by Muscovias in Poland in 1978. And also there was a debate started around that time that CMEs are 3D bubbles or flux ropes or a combination thereof. And that started around that time with Skylab data. So here is, for example, the plot showing the CME rate, and this is the sunspot number, and you can see a good correlation between the two. And this is an observation of proton temperature, proton density, and proton speed, and you can see a shock here. And this was an observation made by, can somebody say, Pioneer 9, and this was Pioneer 9 was at 0.98 AU, and there was a CME observed by Skylab on September 7th, and he was able to make this connection. So, and also he noted the depletion in temperature around the time of the CME, and he associated that depletion is caused basically by particles trapped in magnetic structures. So this is kind of first observation which showed the connection between solar CMEs and the interplanetary disturbance, which we call the ICMEs now. And this is the Kaler's idea. He looked at 16 Skylab CMEs, and the 14 of them were associated with solar energetic particle events, and he found a correlation between CME speed and SCP intensity. The faster CMEs produced bigger particle events, and from that he suggested that there must be a shock ahead of the CME, which is basically accelerating these particles. And here's a cartoon. So you have the CME and the shock, and this shock accelerate particles which propagate along Parker spiral idea. This was of course amplified by another paper by Cliver et al. When they applied these energetic particle events to GLEs. So GLEs are also energetic particle events, except that you see very high energy particles from this event, like GeV particles. Okay. And this is the idea from Muscovius in Poland, where they thought the CME must be a flux rope, which both has a axial component and azimuthal component of the magnetic field. And so they also suggested that this kind of structure actually is 3D, even though people call these planar loops, it actually is 3D because it's a flux rope. So he applied this his ideas to the 1973 Augustine Skylab CME, and found that the theoretical idea that the width of the loop, this one, must be proportional to the distance from the sun center, and also the radius of curvature of the frontal loop must be going with R. And finally, they estimated that the field strength in this flux rope must decay as R to the -2, which is slightly different from a dipolar field, which is R to the -3. But this is a very important connection to the magnetic nature of the CMEs. And you can notice that what Gold thought this is just a tongue of magnetic field, but these guys thought this is actually a rope. And this is the modern picture. Now we have other evidences to show that the CME is actually a flux rope. And at the same time, observation from Mauna Loa, ground-based chronograph, Fisher et al. Created this ice cream cone model, which is different from this. This is kind of an asymmetry in the two directions, but here they thought it must be like an ice cream cone. And but the reality actually must be something in between. And also people were not separating the shock around the CME and the density structures. When you have a flux rope moving out, it causes disturbances around it. All those things are put together as this ice cream cone. So I think they both are right. You can say that you had a situation where the two types of models can be reconciled as a 3D structure. And then came Solwind chronograph. Solwind was operating between 79 and 85, 6 years. And it made very important discoveries, including the halo CMEs, for example, even though it doesn't look very great, but I just drew this red line to show the CME surrounding the sun. And these were discovered by Howard et al. In 1982, this one. And there are several other discoveries like statistical association between interplanetary shocks and CMEs. This is building upon the result by Gosling, who first, for one event, he showed the connection between CME and interplanetary shock. And Shealy et al. Did statistics. And also, for the first time, a high latitude CME was discovered. You know, so far I was showing a sunspot number, which is actually a low latitude phenomenon. Sunspot are confined to, you know, plus minus 40 degrees. But he showed the CME coming from the high latitudes. And that has very interesting implications. I will come to that in a second. So also CME acceleration, deceleration. So between Sun and Earth, CMEs can speed up or slow down depending upon how they interact with the ambient medium. And also the connection between CMEs and GLEs was shown by Cliver et al. So here is one event which I skipped, unfortunately. Yeah. So this very nice CME coming observed by Solwind, and Helios was located somewhere here. So this CME was observed as a limb event. That means you can measure the speed without projection effect. And the spacecraft sitting here saw this same CME hitting the spacecraft. So from that, they were able to make the connection between the two, and also the transit time and slowing down and things like that. And Russ Howard showed that the halo CMEs are actually like regular CMEs, but you're looking at in this direction. And this is the occulting disk of the spacecraft, I mean the telescope. So you're seeing the CME like this. So this is the occulting disk, and that's the halo CME. I think it's an excellent explanation. And the high latitude CMEs. So normally you expect CMEs to come from the equatorial region, or if it is a halo CME, something like that. But Neil Shealy found that there was a CME going just near the North Pole, and he couldn't find the source. He did not know where it was coming from. So I hope you can see the CME. That's the CME. So, but he did suggest that it must be coming from polar crown filaments. You know polar crown filaments, right? The filaments happening very close to the polar north and south pole of the sun, and these happen around the time of solar maximum. Here's a plot from Fujimori et al. Fujimori in 1984. Each tick in this one corresponds to the location of a prominence. You remember prominence? We talked about it. That forms the interior part of the CME. Each one of these prominences is a potential source of CME, because when prominence erupts, you have a CME around it. So Neil Shealy suggested that this kind of high latitude CMEs may be due to eruptions from these high latitude prominences, which happen only during the maximum phase, right? So this couple of years around the maximum phase, you get these high latitude CMEs. This is kind of related to the dynamo phenomenon, because when you have sunspots decay, the trailing polarity flux moves towards the pole and builds up the polar field. And when you have some polar field already near the pole, and if you have new flux going towards the pole, there is a boundary between the two, and that's where you see the prominences. So I think he correctly identified this, and in fact his CME was located around this location. I mean, if you go back to the sun, it's somewhere here. And now we know that these high latitude CMEs are very important, because only when these prominences erupt in the form of CMEs, you can have the sun reversing its polarity. You know, the sun reverses its polarity every 11 years. It happens during solar maximum. So the field becomes north-south to south-north and vice versa. And it happens in both poles. And here's a plot from one of our early papers when Alejandro was a postdoc at Goddard. We found that the polarity reversal takes place at the time of high latitude CMEs. So this is time versus latitude, and the high latitude CMEs are shown here, and low latitude CMEs are from the sunspot region. And you can see during maximum phase, you have this lot of high latitude CMEs coming. This is same as the eruption of these filaments producing high latitude CMEs. And this is very important because this gives a very nice observation to connect to the solar dynamo. And of course, you have not only all the radio and white light observations, they also have white light observations from a different source. These are the photometers on board Helios spacecraft, and they observed CMEs far, far away from the sun in the interplanetary medium. And this is a paper from Richter et al. In 1982, Jackson 85. They used the Helios photometer records to show this kind of CMEs moving away from the sun. And IPS observations, as I mentioned in the beginning, these are interplanetary scintillations. As you know, between sun and earth you have the solar wind, and you also have CMEs coming. But then far away in the galaxy or even beyond, you will have radio sources. When we observe using a radio telescopes, these radio sources pass through the solar wind and CMEs. And if there is no plasma, you won't see anything. You will just see a radio source. But when you have a plasma and moving, it's changing. So the signal from the radio source, which is a plane wave, get distorted. And by measuring this distortion, actually you can infer the properties of the solar wind and the CME. And that's what the IPS technique shows. For example, this is normal situation, and when you have a CME going, use these kind of a pattern that you see in the interplanetary medium due to the scintillation. Scintillation is very important. It's simply because the radio signal is affected. This you will know in a stellar observation if you go in the night and see the stars twinkle, right? That is actually a scintillation in kind of. But on the other hand, if you see a planet, you don't see the scintillation because they are big. The size is finite size. You don't see it. Point sources have plane waves, so they get distorted. Or the other way to look at is you go under the swimming pool. You just lie down and look at the top. Suppose there is a sun up there. If there is no disturbance on the top of the swimming pool, you see the nice sun. But if there is any waves, you see the sun broken up into pieces, right? So that's a kind of scintillation. So there are several works starting from the time of Watanabe et al. In 1973, Gapper, and now you have a very nice telescope in India, in Japan, and now you have Mhd coming on board. And then came the Solar Max Emission, where there was the observation was, of course, a little quadrants, like they observed a quadrant at a time, so they were not able to see the big CMEs, and the field of view also was limited, but they were able to make a good connection between CMEs and prominences, and also the three-part structure. For example, if you here you see a prominence going, so here, so this is the CME, and the inside is the prominence. This is a very important connection. Also, they did not observe many halo CMEs, again because of the limitations of this experiment. Also, the close to sun observation meant that the CMEs increase in speed. So if you observe here, they were faster. If you observe here, they are slower. And if you make the connection, if you do not make the connection, you will see that there's discrepancy. But actually, there's no discrepancy. Here they are slower. They continue to accelerate and become faster over there. And this was shown by Howard in '87. And also more CMEs were associated with GLE, so the connection became much stronger. And this was one of the first cases where crew went to repair the spacecraft. In 1980, it was operating for some time, and then some problem with the attitude control. So it didn't work for some time, and so 3 years later, the space station crew went up there. They captured, repaired the attitude control system, and then redeployed it, and then it worked for another 5 years. And I wanted to show this because this was one of my first CME observation, but not from white light, but from radio. There was imaging made at Clark Lake Radio Observatory in California. And this is the sun in radio wavelengths at 73.8 megahertz. You know, it looks a little bit elongated because you have a streamer here. And then sun is bigger because you cannot go beyond the plasma frequency, right? So that's why it's bigger. But then we saw this very nice change happening here, and we made a difference. We saw that very nice CME here. And we were able to show the connection between this CME and a CME observed by SMM. That's why I show here. So this is because CME is a coronal plasma. It has got 1,000,000 degrees. It has some density. So it should produce free radio emission because of the temperature. And that's exactly what we are seeing. So very nice observation is like thermal emission from CME. Okay, so then the interplanetary observations again by Burlaga et al. They had multiple spacecraft observing solar disturbances, and they were able to construct a picture like this based on observations from several of the satellites, Helios, and let's see, here's Helios 2, IMP 8, and Voyager. You know, Voyager in 1970s, it was still close to us. Now it is you know, gone into the interstellar, close to the interstellar medium. But they were able to use all these observations to show that you have this structure which they call magnetic cloud, which is basically this structure, and then a shock, this structure, and this in between they call it a sheath, which is important because here we have simply there's nothing in between in the original concept. But you know, you have the solar wind plasma there, and it is compressed by the shock. So you have a higher density here compared to the ambient medium. That's why it's called a sheath. And also this sheath can have fluctuating magnetic field, and that will have actually impact on the magnetosphere. I'll come to that in a minute. So he also inferred that the magnetic cloud here must have a structure, helical structure like this. So if you cross this structure like this, you will see a rotation of the field, helical field. And that was an interesting observation, and it is actually consistent with the Muscovius and Poland magnetic flux rope we saw near the sun. And then I consider this as one of the important connection between sun and earth. So this is the magnetic cloud I was talking about. When you go through the magnetic cloud, the field will decrease, goes to the south, and then go to the north. So we have this south-north type of rotation. And so this is the one I showed you before. So if you go through it's like this, field is south here, and then you cross the center of the flux, then the field is north, south-north. This is a kind of magnetic cloud we call. And Wilson found that whenever you have this southward field, the DST index went to negative. This is the geomagnetic storm, right? So the southward component of the magnetic cloud is responsible for the geomagnetic storm. This is the real physics finally we are coming to. Of course, previously from Dungy and Fairfield and Cagle, we already knew that you need southward field to cause geomagnetic storm. What Wilson did was he identified the southward field coming from the magnetic cloud. That's a very crucial step in understanding the connection between CMEs and geomagnetic storms. And then, of course, later on, Zhang and Burlaga applied this to many types of clouds and CMEs, in addition to this one type of cloud that Wilson did. And then there's a very interesting paper by Gonzalez and Surutani. In addition to the southward field coming from the magnetic cloud, they also found southward field in the sheath region that is between the shock and the CME, which Burlaga identified. So in Burlaga's sheath, Gonzalez and Surutani found southward field. This can happen when you have a fluctuating field in the heliosphere, and if you have a CME passing between the shock and the CME, you have the sheath field, and when you compress it, the magnetic field can go up, right, up and down. But the down part is important because that again can cause geomagnetic storm. So this is called the sheath storm, and that is an important discovery by these people, where you can see the sheath can cause geomagnetic storm. And here I have illustrated it. So here's the flux rope, and here's the sheath, which have got upward field and downward field, and that's the shock. When it comes towards Earth, and you have the blue is the geomagnetic field is north pointing. Whenever you have south pointing field, they reconnect and produce the geomagnetic storm. Okay, so all these activities finally culminated in this paper, famous paper by Jack Gosling, who said that CMEs are responsible for geomagnetic storms. CMEs are responsible for energetic particles because of the shock. So CMEs must have the central part, not the flares, because flares are electromagnetic emission. The only space weather effect they have is the electromagnetic flash ionizes the increases the ionization in the ionosphere, so they can cause communication issues and so on. So he was able to make this distinction. Of course, he got into trouble because a lot of people attacked him, saying that you're trying to destroy flare physics and this and that, but actually he correctly pointed out. And he also said that you should continue to do flare studies. He says, finally, the foregoing should not be construed as a suggestion that solar flares are unworthy of study. But despite this statement, people attacked him, but that's okay. All right. So last few slides. We started a few minutes late. I think you're okay if you're hungry. All right. So then comes SOHO, and SOHO has an excellent set of telescopes. It was able to observe up to 32 solar radii compared to 10 to 15 in the past. So they were able to see a lot more CMEs, higher dynamic range, so you can see a lot more details. And and also at the time of SOHO, you had the WIND spacecraft launched, and they were observing from the same. WIND was observing from L1 point, local in situ observations, and SOHO from L1 observing the sun. So they were able to make a lot of these connections. And the radio instrument on board WIND was able to observe the type 2 bursts, namely shocks coming from the sun, and these shocks can also be simultaneously observed by SOHO. So they had an excellent opportunity to do a lot more studies. And one of them, for example, so there were 700 halo CMEs observed, whereas SolWind observed only about 20 of them. So that was a novelty, but now this is a commonplace. And they are very important, halo CMEs, because they are coming towards us. They cause space weather effects. And also, there are many of them. I don't want to go through all this, but I just want to point out the CME cannibalism, only because I discovered it, so I wanted to highlight it. There are many other important discoveries. So this was basically one CME slowly going, and the next CME, bigger one, can come and interact with it, and that results in enhanced radio emission and enhanced particle acceleration. I think that's a very interesting thing, because previously people always consider CMEs in isolation. They're separate ones. But you have a slow CME, a fast CME can really capture it, right? So here's a movie. It's a slow CME, fast CME, right? So that's a slow CME, second fast CME. At that time, you have a big enhancement in radio emission. This is a type 2 burst, and you see this bunch in enhanced radio emission. That means you should have more energetic particles accelerated at the time of interaction. This has led to a lot of interesting simulations and studies, and there are tens of papers on this right now. But I just wanted to give you a flavor of that. And that is interesting because we know cannibalism happens not only near the sun, also in the galaxies, right? Two galaxies can merge, and they call it galactic cannibalism. Here's another, I have some movies, but I don't have time to go through that. Here is a plot which gives a summary of all the SOHO results. This is the speed, and this is the number of CMEs with speed exceeding some value. So essentially, this is a cumulative distribution of CMEs. And you can see there are lots and lots of little CMEs with speeds of 100 kilometers per second. But when you go high in speed, like around 1,000 kilometers per second, you only have about 1,000 CMEs. And these are the CMEs which are important for space weather, because we know that these high-speed CMEs are associated with SEP events, GLEs, interplanetary shocks, magnetic clouds, and geomagnetic storms, and so on. So all these space weather effects are caused by these big CMEs. So SOHO demonstrated that you have, lots and lots of these big CMEs, and but there is a speed limit to the CMEs. You don't see CMEs much more than about 3,500 kilometers per second. Right? Why not? Why not you have a 10,000 kilometers per second CME? Why don't you have 100,000 kilometers per second CME? That's a very interesting thing. But in stars, people have observed, bigger flares, super flares. Of course, they cannot yet observe CMEs. But if these flares are 100 times, 1,000 times bigger than solar flares, the CMEs must be bigger also, because typically the CME kinetic energy is 10 times the flare energy. So I think the explanation is that the sun is capable of doing only certain this much, because the sunspots are of limited size. You don't have a sunspot filling half the sun, right? You normally have a, Earth size or a few times Earth size. So there is a limited size of the sunspot. That means the magnetic field in them also is limited. You take the sunspot area, make a volume out of it, and then you take the magnetic field in the sunspots, and then you combine these two, saying that, okay, the biggest ever observed active region or sunspot region should have the highest ever observed magnetic field. So B squared by 8 pi times the volume will give you a potential energy, and that is the maximum energy possible, and that's why you have a limit, because we have the maximum area is like about 5,000 microhemispheres, and the maximum field strength is about 6,500 Gauss. If you combine these two, you get an energy maximum about 10 to the 35 to 10 to the 36. And we have already observed CMEs up to 10 to the 33 ergs. Of course, when you cannot just keep or store the entire energy in an active region, and also in the process of storing, you may not be able to hold it, because CMEs might keep popping out. So I think it is a good explanation based on basically the size of the magnetic field and the area of the magnetic field that you create on the sun, the dynamo process. All right, one last point about the shocks. All these times we are inferring shocks from type 2 burst, but we never observed in white light. But Neil Shealy in 2000, using SOHO data, showed this weak structure surrounding the bright CME structure. You probably can see it here. He identified this as shock. I think that's a very important discovery, because there are many papers afterwards which showed that very nicely that there is a shock surrounding the white light CME. That will complete the picture of the CME that we saw from Gould's picture, where you have a CME and then a shock. And that is actually shown here. You see that's a white light CME, and you have this diffuse structure around it. That's the shock, which resembles this original structure. So I think this slide basically tells you that the evolution of a concept, interplanetary observation to solar observation, which completes the picture of the CME. And again, stereo had lots and lots of interesting discoveries. And one of them is that the halo CMEs are actually a regular CME, but viewed differently. So for example, when you view from Earth using SOHO, you see the CME surrounding the occulting disk, but at the same time, simultaneously, you observe from stereo B, which is behind Earth by 60 degrees, and stereo A ahead by 60 degrees, you see a CME going out like this. So you can see the 3D structure, which basically like this is the halo CME, and this is the limb CME and limb CME. This is a very nice demonstration of the 3D nature of the CMEs. And also now we can, using stereo, you can see from all the way from the sun, disturbance propagating and hitting Earth. So we now know that this is a huge phenomenon, starts at the sun, and it can affect Earth and then go much beyond. So I think I should stop here. Thank you very much for listening. Sorry, I exceeded.